Start.
Hello, this is our CS230 course project presentation on the topic branch prediction with graph analytics. The team members are I am Deepasha.
Hi, I'm Shubham.
And I'm Om.
Moving to the LTage that we had read from the paper. LTage is a branch predictor algorithm used in computer processes to improve their performance by predicting the outcome of conditional branches in a program. Tage uses multiple tables, each with different numbers of entries and lengths of history. The tables are organized in a hierarchical manner, with the higher level tables having more entries and longer history lengths. The tables are also tagged with different number of bits, which helps to distinguish between different branches. In addition to traditional history branch predictors, Page also uses geometric history lengths. This means that the length of the branch history is determined by geometric sequence rather than a linear sequence. This helps to improve the accuracy of the predictor by capturing long-term patterns in the program. Moving on to the implementation of LTage, we implemented the three parts presented in the paper, that is the buy model, the Tage, and the loop predictor. We used bit sets to simplify the working with the bits and to reduce the memory usage instead of using any kind of other data structure that occupies a large memory. The Tage part was referenced from the original implementation from Professor Andre. We use the same hash function that was given in the paper, and we also use the graceful reset of the use goods as suggested by them. We almost implemented all the features like the use alt variable. Uh, we used a global history length of 1024 bits and the path history length of 16. That is, we use the PC value, the global history length, and the path history length to index into the components of the page. And this was done using the hash function. Smallest history length used is 3, and there's a variable called history alpha, which is equal to 1.7. And this variable is used for getting different history lengths across all the tables. We reset the useful bits after 256,000 branches, and the loop table size is of 512. The max iterations tracked were 1024.
Okay, now I'll be talking about the improvements that we made. So firstly, we saw that loop predictor was not being used very often, and this was because the confidence threshold was very small. So the first thing, sorry, the confidence threshold was very big, so it wasn't reaching the max value. So the first thing that we did was we decreased the confidence threshold. This allowed for the loop predictor to be used more frequently, and it showed us better results. The next thing that we did was we increased the number of components that were there from 12 to 15. This allowed us to store more data and have a larger history length, which eventually gave us better results. Next we did was we increased the predator counter bits from 3 to 5. This allowed us to have more levels in our prediction. Like we were checking the strong condition, and this allowed us to have a more stronger condition while we were branching. Next, what we did was in the loop part, there was a variable called with loop, which decided whether to use the loop predictor or the taste predictor to make the prediction. So we decreased the value of the variable with loop, which again allowed for the loop predictor to be used much more than the taste predictor. This also gave us a better score, better accuracy. After this, we went to decrease the maximum age of the loop predictor, which means the entries in the loop predictor were refreshed more often. And this, like again, improved our results. Um, we then changed the number of bits of index and tags that we were storing, and we increased them by what they were before. And we saw that there was some a trend that was given in the paper, something like 7777888 something, and we modified that and we tuned it according to like graph analytics, and we found the accuracy to increase. Lastly, what we did was we saw in the default bimodal predictor, they had initialized all the like bits with strongly not taken, but instead of that we use weakly taken. This showed a significant improvement while the first when the branch was selected for the first time, when the bimodal predictor was used. Yeah, that's all.
Uh, yeah, now I'll talk about the insights, major insights that we gained. So the very first insight was the hash functions are really significant in determining the accuracy. That is because earlier we were using a very simple hash function, which caused a lot of collision while indexing. So the accuracy was very low. We then actually looked at the original implementation and used that hash function, which increased our accuracy significantly. So hash function is very important. That's the first insight. And the second one is that the loop predictor did not improve the performance by much in the original implementation, because it never reached the confidence threshold that they had set, which was very high. So what we did was, in graphs, loops are a very common occurrence. So we decreased the confidence threshold, and also the loop prediction was also considered valid if the past iterations were greater than some small number, which we chose to be 32. And this also improved the accuracy of the predictor. So now some data. Uh, we have used five traces. Sorry, we have used five traces, and we ran hash perceptron. Our first implementation stage without any of these improvements that Om talked about. That and our optimized, our final version. So as you can see, there there's a significant improvement between between normal, our first implementation, and our optimized version, which will be more clear if I go to accuracy. So these are the plots. This is IPC and miss per kilo instructions, and yeah, accuracy. So as you can see, there's like a difference of 1 or zero point 0.5 almost in our optimized version and our original implementation, and we are able to almost reach the accuracy of hash perceptron, while hash perceptron is still performing better, marginally better
Yeah, the
on
CC trace was a
traces.
little.
So yeah,
Yeah,
this is
our model just
this is our
performed a little worse in the CC trace, I think.
yeah, it is significant in the CC trace. Like there's a point 0.5 accuracy difference, but the rest are very close. Two decimal places here, two decimal places here, and again two. It is same to two decimal places here. So yeah, this is our implementation. Thank you.